Okay, so today we're going to still talk about, it's still going to be a little more MR physics space. We'll start getting into some of the biophysics of fMRI. So this will be the last sort of full lecture for a while on physics. And we will then transition more into signal sort of data processing starting on Monday. And then the next physics lecture will probably be when we do diffusion, because then we'll have to talk about the physics of diffusion. Okay? So if physics is not your cup of tea, bear with me. But what I'm going to go over today is some basic concepts that are going to be helpful for you to know, especially if you're doing a lot of neuroimaging. It's useful to know what all these things mean so that you have some idea of what you're doing. Okay. So let me just start. Could you get the light, Frank? This was the movie that didn't play last time. And just to remind you, what we're going to have here on this side is the K-space representation, and this is going to be the image over here. All right? And you can sort of see that when you only have the center part of K-space, you only have what are called low-frequency information about your object. Okay? So in MRI, what we need to do is we need to cover get enough information in K-space so we can make a nice image. So I'm going to play the movie, and what you're going to see is as we acquire more and more of the K-space information, that image will become more and more clear. So hopefully it'll play today. It played when I tried it earlier today. So that's you're seeing as we go, and I'll play one more time. As we go out and collect those outer parts of the K-space, we fill in the details of our image. And so the job of the MRI physicist or the MRI pulse sequence programmer is to cover K-space and get all that information in an efficient manner. And we'll talk a little bit about for anatomical imaging, typically we go through K-space line by line by line by line, and it takes some time. In fMRI, we actually zoom through very quickly, like that. Okay. Whoops, didn't want to play that again. So the concepts we're going to do today is we're going to switch gears a little bit. We're going to talk about relaxation. So we're going to talk about something called T1, T2, and T2 star. We're going to talk a little bit about the imaging parameters like echo time, repetition time, flip angle, that when you go on the scanner, you'll see all these things, but maybe you didn't really know what they meant. And we'll talk a little bit about how you want to set those. And then the second half of the class will start transitioning into fMRI. Right? Okay, so to remind you, for the MRI experiment, we start off with the magnetization aligned with the magnetic field. And then we use an RF pulse to flip it. Okay? And for now, we're going to assume we flip it 90 degrees. So that's showing my pencil is flipping 90 degrees. And then it's going to process around the main magnetic field. All right? Now, nothing lasts forever, so it's going to die away. And so we want to talk that process of that dying away is called relaxation. Okay? So there's two main things that's going to happen. One is this is its equilibrium position. So it's going to want to return to this position. Okay? So we excite it, it does this, but eventually it's going to go back to here. All right? And that process is fundamental to all of MRI. The decay of the magnetization is called free induction decay. So when you hear the term FID, that's what it refers to. And one of the things is, as you notice, the signal, it's oscillating back around, and as it's doing it, it's sort of dying away. And this happens with an exponential decay. And this sets the limit of this is the time we have to collect the data. Okay, so this is typically about 40 or 50 milliseconds. So it's much less than a second, and so that's why in MRI we're always trying to go as fast as possible, because as soon as we create the signal, it's dying away, and we have to capture the signal before it dies away. Okay, so there's two main types of relaxation. There is what's called longitudinal relaxation and transverse relaxation, and they have time constants, T1 for longitudinal and T2 for transverse. So we're going to talk about both. So T1 is longitudinal relaxation. And that's basically this idea that I start off with an relaxation here, right? When I tip it over to here, then there's zero component here, right? So the growth back of the Z component is the longitudinal relaxation. Okay, so going back to here it's sort of this part grows back to where it was. So that's longitudinal relaxation. And that's really important because each time when I flip the magnetization over, how much signal I have depends on how much has grown back. Okay, so if I flip it, then here there's nothing else to flip, right? So I have no more signal. If I only wait a little amount of time for it to recover, then there's not much signal to flip over. So ideally, I want to wait for the magnetization to grow back fully and then flip it again. Okay, so that's the first thing we're talking about is longitudinal relaxation, and the recovery is exponential. Okay, so it has an exponential constant. Time constant is t1. But for the purpose of this class, just realize it just takes time for the magnetization to recover. Okay, and so that's why we have to wait around sometimes. And that's why does a scan take so long? Part of the reason is because we're waiting for the magnetization to recover, so we have enough magnetization for the next shot. Right. The other thing that why T1 is important is because that's the basis of a lot of our contrasts. So those of you doing like an MP RAGE, your T1 weighted image is basically called T1 weighted because it's making contrast based on the different T1 values. So if you notice in this graph, gray matter and white matter have very different T1 values. Okay, and so that difference in T1 value, this is T1 as a function of field strength. So that difference in T1 is what allows us to create a T1 weighted image. If there wasn't a difference in the T1 between the two tissues, we wouldn't be able to create that contrast. Okay. The other type of relaxation is called transverse relaxation, and that's basically when we tip this magnetization over. Okay, then this is the signal we have to deal with. All right. But what happens is the length of this magnetization gets smaller and smaller and smaller. It's like a death spiral; it sort of dies away. Okay. So if we imagine the magnetization starting off here with a very big length, it sort of dies away, and so that's the signal dying away, right? And so we have to capture the information before it all dies away. Right? So there's really two processes. There's a dying away in the transverse plane, and there's a regrowth of magnetization in the longitudinal axis. All right. Okay. So the free induction decay is that, and so it has a decay of e to the minus t over t2. So it's an exponential decay. All right. And the way to think about it is we start off with some magnetization here, and in any given voxel you have lots of different spins, and they're all sort of interacting with each other, and they're all sort of causing each other to get out of phase. And that dephasing is what causes the T2 relaxation. So you can sort of, this is from one of your readings, and they're showing you each of these is a different sort of spin, and they all add up to give you this black spin, this black magnetization. As they get more out of phase, then that black arrow's length gets smaller. So that decay of that arrow's length is because all the spins are sort of getting out of phase. Okay. So phase is an important topic we'll also talk about when we talk about fMRI and diffusion. And once again, the reason we care about T2 is because different tissues have different T2. So here, I believe this is at 1.5 Tesla, there is a difference in the T2 of gray and white, and you see CSF has a much longer T2. Okay, so that means if I excite the magnetization in the cerebrospinal fluid, it will last for 4 seconds, okay, or more. Okay, whereas if I do it in gray matter or white matter, it's mostly gone after a few hundred milliseconds. Okay, so this is just a plot that summarizes what happens. So we're looking at the magnetization. This is here in the transverse plane. You're sort of seeing that you'll see this death spiral, and let's just see what it does. Place. So this is the transverse, and this is the longitudinal. Okay. So the thing to keep in mind is things die away. This is the T2 decay, and this is the T1 recovery. All right. So let's play that again. So you have decay for T2. And then the recovery is T1. All right. And what that looks like here is if I start the magnetization here, it sort of spirals around, and T2 is always less than T1, so it spirals around, mostly dies off, and then sort of does most of its regrowth later. Okay. So that's the basics of T1 and T2. Any questions before we? Yeah.
For T2, the timing, how does that translate to the resolution between, like, let's say, white matter and gray matter?
Yeah, that's a good question. So in general, you can think of resolution separately from the decay unless you're acquiring the data over a long enough time period where the T2 actually matters. Okay, so in that case, it would cause some blurring. Now, in some cases, the T2 is really short. Like the T2 is really short in your bone, in which case you don't even see the bone in MRI unless you use a very short, what's called, we haven't, but there's something called echo time. Okay, so so in that case you have no resolution because you can't even see your object. So if you're let's revisit that when we get to echo time. Okay, any other questions?
Will there be a difference, like when you acquire the data, different decaying time, like because the curve is like pretty long?
Yeah, so we'll get into that in the next few slides. So we'll introduce that. So that's a good question. So basically, T1 and T2 are sort of the intrinsic properties. The next thing we'll talk about is T2 star, which is much more related to fMRI. And then we're going to talk about something called echo time and repetition time and flip angle. So T1, T2, and T2 star are determined for you by nature, and then you get to pick echo time, TR, and flip angle. Okay, so there's 3 things out of your control and 3 things within your control. Okay.
Small question.
Yeah.
Is there any reason to have like the longitudinal magnetization as a T1 and a T2, the naming of a T1, T2?
That's a great question. I actually don't know the answer. Why it's T1 and T2. Maybe one was discovered first. I don't know.
But for functional and structural, we collect the kind of the recovery different or separately, right? So how this works? Like for structural data, we only say the T1 was T1 star, right? In that case, so we separate the 2 processes. There's 2 processes.
Yeah, so we'll talk a little bit about contrast in a bit. Yeah, thanks. Okay, so the next thing we want to talk about is something that's called static inhomogeneities. And what this means is, we pay a lot of money for the magnets. Like, for the magnet itself, it's maybe $2 million, right? And so, and the idea is when we buy the magnet from the manufacturer, we want a very uniform field. Okay, we want, like if a 3 Tesla, we'd like it to be 3 Tesla everywhere. Okay, so we put all that money into it, but then the funny thing is that once you put a head in there, it all gets distorted again. Okay. And the reason for that is if I have a uniform magnetic field, so this here is a uniform field, okay, so that's what you pay the $1 or $2 million to get this nice uniform field. That's also when the magnet is doing shimming, it's trying to make the field more uniform. Then if you put an object into that, so objects can be either diamagnetic or or ferromagnetic, it will tend to either concentrate the field or repel the field. Okay? And so what that means is once you put a head of human body in there, the field gets distorted again, such that different places in the head are now going to have different fields. Okay? And so here is an example of this. So this is a picture of the field. This is what's called a field map, which some of you have seen before on the scanner. And this is showing that the fields sort of towards the front of your head are very different from the fields in the other part of the head. Okay, so why might the fields be so different at the front of your head? Go ahead.
Different tissues.
Different tissues is specifically what different tissues? The what? The eyeballs, yeah, possibly, but there's even a bigger thing that you have at the front of your head. The skull? Sinuses, yeah. So the main thing is the sinuses. You have these big air pockets, and so the magnetic properties of air are very different from the magnetic properties of tissue. And so you're going to have, the fields are going to be very distorted. And when they're distorted, that means, remember, if we go back to our Larmor frequency, omega equals gamma b, if I have so the rate at which the spin's processed depends on the magnetic field. So if I have very different fields in different parts of the body, or even within a voxel, I might have very different fields, then we're going to have spins operating at different frequencies. Okay? And so what that leads to is something called signal decay. So let's do a thought experiment. So let's say we start off with these 6 spins and we tip them and they're all aligned. Okay? So if we have these 6 spins, they're going to sum up and give us this really nice long blue arrow. Okay? We just add up those arrows. Now we wait some, here we're introducing this thing called TE, which stands for echo time. Okay? And in addition, in general, in MRI, and we'll get into the reasons later, we wait some amount of time before we actually acquire the data. Okay? Now, if there are non-uniformities, so this is just a picture showing that the field might be not uniform, then spins in different places are going to process differently. Okay? So some will be faster, some will be slower, and as you see, they get out of phase such that when we sum them up, that length of that blue arrow is less. So that's the signal decay. And this is what we're calling sort of our T2 star, leads to our T2 star decay. All right? Now let's say the inhomogeneities are even greater. So this is greater inhomogeneity. Okay? Then what that means is the much more different across space. So then the spins are got to get even more out of phase, and you see that arrow gets even shorter. So in this case, there's a lot more decrease and dephasing. Okay, so this would have what's called a shorter T2 star. Okay, because it's going to decay faster. And this same process is actually the basis of fMRI, and we'll talk about that towards the end of today. Right? So the way we describe this is now our time constant is now a T2 star. Okay, so T2 star is the effective transverse relaxation rate. It's basically how fast things actually decay. And it's composed of 2 terms. It's composed of the T2 term, which is just due to random dephasing, and it's due to T2 prime, which is this static dephasing. Okay? So the good news is if you want to, you can actually get rid of this term with something called a spin echo sequence. This term here stays, okay, because it's random, so there's really no way to undo it. But this term here, the T2 prime term, there is something we can do about it. Now, we don't always want to get rid of it, and for example, in fMRI, actually you're going to keep this term. But for things like making a nice T2 weighted image, you might want to get rid of that term. Okay, and we'll take a look at an example of that. So here are some examples of if you don't get rid of that term. These are susceptibility artifacts. So this here is a person who has obviously no mouth or teeth or jaw, okay? Or does she or he? Okay. So what do you think? What's your diagnosis here? This person comes in and gets this scan done. Are you going to send them to the doctor or no? Why not? It's probably just dental work, right? This is probably a teenager with braces. Okay. But because the metal causes distortions of the magnetic fields, it causes all those spins to dephase and the signal to go away. Similarly, this person probably has some metal implants. Okay. So even though it may not be a safety issue, it's obviously not good for image quality. So when you're doing your exams, obviously the most important thing is safety, but a secondary consideration obviously is your images aren't going to look good. Okay. So it turns out there is a trick that you can play. It's called a spin echo. And what that is let's say we start off with our all aligned. After some amount of time, it gets out of phase. And so this spin is fast, this spin is slow, okay? And this one is like just right, okay? And then what happens is, if at that point, let's say you had a race, right? You had one person's really fast, one person's really slow. Halfway through the race, if you make the fast person go to the end of the line and the slow person go to the front of the line, and then you wait, let's say you ran the race for like 10 seconds, right? And that fast person's here and the slow person's here, and then you make the fast person go to the back, the slow person go to the front. Now you wait another 10 seconds. What's going to happen at the finish line? So let's say the fast person was ahead by 10 feet, and then you made them go back 10 feet. So they're back, they're 10 feet behind the middle person, and then the slow person fell back 10 feet, but you put him ahead by 10 feet. And then at the end, they're all going to align again, right? They're all going to finish at the same time. So that's the idea of spin echo. So in this case, we move this spin over here, and we move this spin over here using a 180 degree, using a radio frequency pulse. Such at the end, everything has been refocused. All right? So that's shown in this picture here, where the spins dephase, and then you flip them, and then they rephase. Okay, so it's a pretty cute trick that was invented in 1950 by Erwin Hahn. Okay. And so with that, so that's now called a spin echo pulse sequence. So we have, in this case, a 90-degree pulse that does the excitation, and this does the refocusing. So this excites, and this refocuses. All right. And so what you end up with is, this is a gradient echo image here, which has these sort of signal dropouts due to those field homogeneities. And if you apply spin echo, they magically go away because we refocused all those effects. So T2 weighted imaging is really very bread and butter in clinical imaging because it's you don't want to have these sort of artifacts, and it is used in some protocols as well for neuroimaging. Okay. Any questions? Okay, so that's sort of the first part of the lecture. And just to remind you here, this is the T1 longitudinal recovery, and then we have both T2 and T2 star decay. And as you can see, T2 star decay is always faster than T2 because T2 star decay consists of both T2 and that additional static homogeneity term, the T2 prime term. And then just to get a sense of how T1 varies with field strength. So these are for gray and white matter and blood here. So T1 tends to go up with field strength, okay? But T2 tends to get shorter with field strength, and T2 star as well. So that's one of the things, one of the challenges of going to higher field strength is things are dying away much more quickly. So when you go to higher field strength, say you go from 3 Tesla to 7 Tesla, things have to be much faster because things are dying away so quickly. Okay. The other thing is T1's getting longer, so not only are they dying away more quickly, you have to wait longer for them to recover back, and so you're up against those things. Now the trade-off is you have much more signal noise, so then that's often an overall win. Okay. Okay, so now we're going to transition into talking a little bit, just to give you a sense of how we create image contrast. And there's two things we're going to introduce at first. There's going to be TE or echo time and TR or repetition time. Okay? And then there's one last thing we'll talk about, which is theta or flip angle. Okay? Initially, we'll just think about theta equals 90 degrees, okay, which is what we've been doing all along, which is we just take our magnetization, we flip it 90 degrees, so it's all transverse. As we move on, we'll look at what happens when theta is less than 90, or when, say, theta equals 180. Okay? But these are, so this, you can typically, echo time is very important, repetition time is very important, and flip angle. So these are three of the major things that you will tweak in addition to what your resolution is, okay, and your slices. So typically, the most important things are you have your slice prescription, you have your FOV, you have your matrix size, and then these are the other parameters that you'll often have to think about how to set them. Okay, so a typical MR pulse sequence looks like this. There's going to be a 90-degree excitation pulse. We're going to wait some amount of time, and then the data is collected here, such that the middle of the data is collected at echo time. And the middle here represents the center of K space, which is that part which is sort of the overall mean signal of your image. Okay, and then the time between excitation pulses is TR. Okay. So that's why MRI sequences are very rhythmic. You're basically doing the same thing over and over again. You're exciting the spins, you're letting them process, you're collecting the data, you wait for it to recover, and you do it all over again. Okay. So this is what's called a gradient echo sequence, because we're not refocusing the spins. Now, if we add an additional 180 pulse that does that refocusing, then this is what's called a spin echo sequence. Okay, I'm not really going to go through the math here, but the only difference between these is this has a T2 star and this has T2. All right. So, but let's talk a little bit about how you might set TR and TE. So here's an example from your reading where the excitation pulses are spaced like this. So this distance here is TR. All right. And these are 3 different tissues, white matter, gray matter, CSF, with different T1s. So you can sort of see if my TR is fairly long. In this case, it looks like it's about 8 seconds, which is quite long. So this is like 8 seconds. Then all the tissues sort of have time to recover. Okay, so that if you look at this image here, there's not much contrast between those images, right? Because they've all basically recovered so that they all sort of have the same signal level. Now, let's look at a short TR. This is now 900 milliseconds. Okay, so less than a second. So in this case, you can sort of see white matter recovers the most because it has the shortest T1. Then comes gray matter, and then CSF is hasn't recovered very much. So now you look at the image. You see white matter is the brightest, right? Gray matter is the next brightest, and CSF in the ventricles is the darkest. So that's really how you sort of introduction to how you can use TR to get T1 contrast. Because the more you wait, then certain tissues will recover more than others, and you use that to achieve contrast. All right? Any questions on that? Okay.
So how do you know what is the optimal PR?
You have to know more MR physics. Yeah. So that's sort of beyond the scope of this class. There are other classes you could take that. We'll get into that. Yeah. Similarly with T2, so the signal is decaying away, and so now you can decide whether you want to require an early echo time, a medium echo time, or a long echo time. Okay. So in this case, we have 2 tissues, one with a short T2 and one with a long T2. Okay. If I acquire with a very short echo time here, neither has decayed very much, so there's not much contrast between them. Okay. If I wait too long, they both decayed quite a bit. So once again, at this place, there's some contrast, but maybe not as much as I'd like. This is from the book. It seems like there is quite a bit of contrast, so I don't really like that example, but we'll have to get a better one for next year. And then here, obviously from here, if I acquired a sort of a echo time that's sort of in between, there's a lot of difference between those 2 images, and supposedly this has the highest contrast. Okay. So that's why when you're doing T2 weighted imaging, you want to pick the echo time such that the difference between the tissues is greatest. All right. So in general, this is sort of, you generally never want to do this. Okay, a short TR and a long T is generally not great. But for a long TR and a short TE, what gets called what's proton density weighted imaging, which is not really used that much, but some protocols do use it. In which case, you're sort of immune to both T1 and T2, so fairly independent. Of both T1 and T2. Okay. T1 weighted image is here, where you use a very short echo time. So neither the tissues haven't really decayed. There's not much difference in how much the tissues have decayed in T2, and a relatively short TR, so you can sort of emphasize the differences in T1. So this is sort of like your MP RAGE sequence. Okay. And then for a long TR and a long TE, or a relatively long TE, you get a T2 weighted image. Okay. And that's why typically if you're doing a T2 weighted scan, they can be much longer than the T1 weighted scans if you really want to have pure T2 contrast. Okay. Now for fMRI, or for most neuroimaging, we actually play another trick, which is, this is the part we looked at before. So this is the spin echo part. What we do is we add another 180-degree pulse before we even start acquiring the data to do what's called spin inversion. Okay, so this is what's called inversion. And let me just give you an example, talk you through why that might be useful. So inversion is this. Here's the spins pointing up. We're going to apply a 180-degree pulse, and they're going to flip all the way back down. Okay? So previously, we started at 0, and we were just recovering like this. Now we're going to start here at negative, and we're going to recover like that. So somewhere on the path to recovery, we're going to go through 0. Okay? So this is what's called a null point. Okay? And that is going to allow us to create even better contrast. We can actually erase the signal from certain tissues by using this trick. So this is shown here, where this is also from the reading, is they've applied an inversion pulse, and so you see as they're recovering, at different times, different tissues go through their null points. Okay, so if I acquired at this time TI4, you notice all the CSF signal is 0. So if I wanted something that had all the CSF gone, I would acquire at that point. At this point here, TI3, all the signal from gray matter is gone. Okay, so it's sort of a cool technique. You can sort of get rid of certain tissues. Okay. So this is used a lot in clinical applications to get rid of like fluid from around tumors and things, so you can sort of see the things you want to see better. And then we'll talk in a few slides about how we use it for neuroimaging for the MP-RAGE. But there's one more concept I want to introduce to you, which is now we're going to think about changing the flip angle, theta. Okay, so far we've only talked about a flip angle of 90 degrees. Now we want to talk about making the flip angle smaller. Okay, and although it's a simple concept, the person who first proposed that I'm not sure how much money he made, but patented the idea and made quite a lot of money out of it. Okay, so here's the basic idea. If I flip the magnetization over, then I have to wait a long time for it to recover, right, to get back to full magnetization. But if I only flip it a little bit, then it has less to regrow, right? And therefore, I may not get back to full magnetization, but I don't have to wait around as long. Okay, so a good useful analogy is what's called sort of the toilet bowl analogy. So if you think about in your home, you might have a toilet has a tank, right? So and the water goes up fully, right? Let's say you have and if you flush all the water away, right, you get a really good flush, right? But you've used up all your magnetization, right? So that's like a 90-degree flip angle. So now you have to wait around for it to refill, right? So you might have to wait 5 seconds for it to refill. So in which case the T1's like around 5 seconds, right? But but you get a full flush, right? So the trade-off you could make is, and you see this like in the airport, they have this, like they have, if you flush one way, it's a full flush, and if you flush the other way, it's a half flush, right? So you could do a half flush, right? So you only get half the flush, but maybe you only need about 30% of the water to do that. So now you don't have to wait around as long to do your next half flush. Okay? So the idea is by changing that flip angle, you can actually go faster. And so what the flash sequence at Insight allows us to do is to make that TR really short. And so that's really useful if you don't want to spend that much time acquiring your image. And so where this comes in almost all your exams is in the localizer scans. Okay, so those of you who've run the scanner know that you put the person in and you acquire these localizer scans that just tell you where the head is. And those are very fast, right? And these are all using this flash sequence because you're not really you're willing to give up, you don't need really great image quality. So what you really care about is going fast, right? So that's using this flash sequence. So this is just an example here where in this case the T1 is 1,000 milliseconds. So if we really want to let things recover back, we'd have to wait about 3 to 4 seconds because you typically have to wait around 3 to 4 the time constants for everything to fully recover to like 98 or 99%. In this case though, if I use a flip angle of, in this case, let's say it's like about a 50-degree flip angle. Okay, so I don't flip it 90 degrees, I just flip it 50 degrees. Now if I wait around for just half a second, I get like half the magnetization. Okay, so I'm able to go like 6 times or 8 times as fast and I've only given up half my magnetization. So in some cases, that trade-off is worth it, because going 8 times as fast is a huge gain, right? Okay. So that's so where you're going to see this concept is both in your localizer scan, and you'll also see it in your MP Rage, which we'll talk about, I guess, right now. Okay. So this is the MP Rage sequence. Okay. So the MP Rage sequence starts off with this 180-degree inversion pulse, right, which inverts the spins. And so it's going to invert the spins, and then as the spin recovers, it's going to acquire the data very quickly in some time, and it's going to use these very low flip angle pulses that are going to go super fast. Okay, so that's the other place where you're going to see this concept used, by just flipping a little, getting a little bit of signal, but means we don't have to wait around as long, and so we can go really, really fast. And so that's the other sequence that most of you will do is the MP Rage sequence, and it's using those two concepts of using an inversion pulse such that you can you see CSF is really well nulled out here, and you have really nice gray-white matter contrast. And then you have these low flip angle pulses. Okay. Now to optimize this, obviously it requires, it's much more complicated, but that's the basic idea. Okay. Any other questions? Okay. And the final thing we're going to talk about before we move on to fMRI is what's called the Ernst angle. And this also comes into fMRI because you'll often wonder, well, why is the flip angle set to this or that? Okay. So for example, in the fBurn protocol, the TR was 2000, the flip angle was 77 degrees. Okay. If you go look at the HCP protocol, the TR was 720 and the flip angle was 52 degrees, right? ABCD has 852 degrees. Okay. So they obviously follow these curves, so there must be a reason. Okay. It turns out that for every TR and T1, there's an optimal flip angle that gives you the maximal signal. And so these aren't just chosen by random. These are actually, people actually calculate the Ernst angle and look at that. So essentially, these are sort of typical T1s for gray matter, between like 1300 and 1600. And so you can sort of see that the Ernst angle is the optimal angle to use to give you the maximum signal. And so you can sort of see that these projects picked their flip angle very close to what the Ernst angle should be. Okay, so it's not just a random choice. Okay, any questions before we get to fMRI? Okay, so mostly what we've talked about so far is more on the anatomical imaging part in terms of some understanding of T1 and T2 and flip angles and TRT will be useful to you as you're sort of looking at different protocols. And then in week 3 is where you're going to start learning how, what the ways of processing the anatomical data are. But that's in terms of MR physics, that's all we're going to talk about for this course for anatomical imaging. So any questions before we move on? Okay, if there's no questions, we're going to move on to fMRI, which, as all of you know, is studying brain function. Okay, and most of you have probably done fMRI, and it's basically like MRI, except sometimes the subject's doing something, or not. Okay. fMRI is a relatively young technology, really started by Seiji Ogawa sort of in the early 90s, and this was sort of one of the first fMRI studies where they shone a light on a person and then looked at the signal in the visual cortex, and the signal went up and down and up and down. Okay. But an interesting thing is they also looked at the effective echo time. So you can sort of see at an echo time of 40 milliseconds, you get a signal. But if you acquire it too quickly, you don't get much signal at all. So we're going to talk a little bit about what the optimal choice of echo time is in a few slides. The trade-off between fMRI is we're going to give up some spatial resolution. And this, I'm actually realizing this is sort of outdated, right? This now voxel volume is like now down to 8, right? Right. So with improvements in technology, since Rick wrote this book, the first edition of the book, that's like a factor of what, 6? That's pretty huge. Okay. So we actually can do now whole brain at 2 millimeter isotropic resolution A lot of that is due to the multiband technology that we talked about on Monday. Okay. And then obviously we're going to go much faster through the brain than we would for, so an MP range might take you 4 to 6 to 8 minutes. That's much too slow for fMRI. We want to be, now the standard protocols are doing whole brain in less than a second, right? And the way we do that is with single shot echoplanar imaging, where we're zigzagging very quickly through K-space. But in modern scans, the other thing that's very important is multiband. And then parallel imaging. And the other thing is multi-channel coils. So it took all these technologies. So when fMRI first started, it was really just single slice imaging, one channel, and that was, you know, for there you were doing 4 millimeter resolution, 2 to 3 seconds. So with all these other additional technologies, most of which were actually developed by graduate students for their PhD thesis, that got us down to less than a second, 2 millimeter isotropic resolution. So the field has actually moved quite a bit. So what is functional MRI? So most of you know, basically we acquire the images during the stimulus, and then we look at, for example, the signal in each voxel, and then we come up with a statistical map. And so the next couple of weeks are going to be talking about the underlying statistics that we'll use to create those maps, and then you can make nice pretty pictures. In this case, the person was tapping their fingers. So the basis of, say, 95% of fMRI, maybe 98% of fMRI, is what's called blood oxygenation level dependent contrast, or BOLD. So typically when people talk about fMRI, they actually mean BOLD fMRI. There's non-BOLD fMRI, but it's not really used that frequently. Okay, we do some here, and we'll talk about some later in this class, but most projects will use BOLD fMRI. Okay. This is the picture we showed before, and here we really want to focus on this echo time dependence. So we're going to spend the next lecture starting talking a little bit about what that BOLD signal is and what are the factors that cause it. So the first thing we're going to do is we're going to introduce this term called R2 star. Okay, just because it's easier to write it in this form, and this is just equal to exp minus t over t2 star. Okay, but it's just easier not to carry around that division all over. And then also, it turns out from the physiological point of view, things are much more related to R2 star. So t2 star you can think of as the time constant. R2 star is like the relaxation rate. Okay, but one is just the inverse of the other. Okay, so R2 star is just 1 over T2 star. So R2 star composed of the R2 term, which is related to 1 over T2, and the R2 prime term. Okay, so fMRI uses both of these terms, but by and large, this is going to be the dominant term for most fMRI. So for gradient echo MRI, this is going to be the dominant term. There is something called spin echo fMRI, but as much signal, no one uses it, okay, except for a few groups that are doing very careful biophysical studies. Now, this may change with late changes in technology or understanding. I know there's some playing around of it here, but it's just the amount of signal noise ratio you give up is just so huge that no one is willing to make that trade-off. So for this class, we're really going to focus mostly on gradient echo fMRI. Okay, so this is the picture I showed you about signal decay. And the idea is just simply that, you know, depending if there are inhomogeneities in the magnetic field, there can be decay, and this decay is what gives rise to the R2 star decay. All right, so that's the physical picture you want to have in mind. We'll revisit this picture later when we talk about deoxyhemoglobin. So let's think about the bold signal change first. So before we get into some of the biophysics, we just want to talk a little bit about sort of how you should pick the echo time and what's the dependence of the bold signal on the echo time. So the idea is that during a baseline state, let's say before you've given the stimulus or shown your checkerboard or had the person do your task, things are going to decay with some rate R2 star baseline. So that's shown here. It's decaying away at some relaxation rate. And then during activation, there's going to be a different relaxation rate R2 star. And for most parts of the brain and most tasks, that R2 star is going to be smaller. So in this case, this picture is showing R2 star during activation is less than R2 star during the baseline. So things are not decaying as quickly during activation as they are during baseline. And so this signal change is your F signal. Okay? And you notice now you sort of see why you have to pick the echo time correctly. If you pick it here, there's no change, and if you pick it here, there's very little change. So the difference of those two has some shape, and you'd ideally like to be sort of at the maximal signal change. All right? So that's one thing that we're going to talk about is how do you pick the right echo time to maximize your fMRI signal. The next thing we're going to talk about is the fact that fMRI, typically we look at the percent change or the percent delta. Okay? So we typically look at the change in bold over the baseline bold signal. Okay? And so that's as the signal during activation minus the signal during baseline over the baseline signal. And it turns out that that is actually related to, can be expressed as minus TE times the change in R2 star. Okay? This is typically less than 0, so that this is typically positive. Okay? But you can sort of see, according to this logic, if you want the more you increase the echo time, the more signal noise, the more percent bold change you're going to get. Okay, so by that logic, you should use as long an echo time as you can, right? Because that's going to increase your percent signal change. So what's wrong with that logic? So that's saying I should go way out here in echo time, right? But we just said that if I do that, then I'm not going to get much difference in my signals. Okay. So what's happening? Why is that term becoming so large as I go out in echo time? Any ideas? So what happens to this term here, this S of B term, as I go out in echo time? What is it going to? It's going to 0. So what happens when I take anything and divide by 0? It becomes really big. Okay, so percent change is becoming big, but it's basically because I have something over 0. So it's really not that useful. So this is useful to know that percent change does scale with echo time, but at some point it doesn't really help you because you have no signal left. Okay. So this, you don't have to go through this, but this is just showing you how we get this percent change having sort of this TE times delta R2 star term. Okay. So what we really care about is actually, the other thing we care about is what's called contrast to noise ratio. What you really care about when you're doing an experiment, when you do the statistics, is how much did the signal change versus my noise? Okay? So let's say the signal change is delta S and your noise is represented by some standard deviation of the noise. Okay? So now you have this delta S can be expressed as, so delta percent change, whoops, is just equal to delta S over your baseline signal. Okay? So you can rewrite this delta S as percent change times S naught. And so you can rewrite it like this. So one way that's useful to rewrite it is the contrast noise ratio is just equal to your percent change, which is often due to like biology, right? And some physics, right? And it's multiplied by what's called temporal SNR, which is your baseline level divided by your noise. And this is actually, this is going to come back when we talk about scanner quality. And also physiological noise, which we'll talk about. So this is something we actually measure every morning at the center, because if this TSNR is not good, then your contrast noise ratio isn't going to be good, no matter how much percent change you have, right? So if your scanner is just inherently noisy, then it's going to be much harder for you to detect anything due to the brain. Or if your scan is really dominated by the person breathing a lot, then that's going to reduce your TSNR, so then it's going to make it harder for you to actually look at any percent change. Okay, so we'll revisit this later, but that's introduction now why TSNR is so important. The other thing we want to talk about is that this contrast noise ratio can be written like this, which has an echo time. It's like TE times the exponential term, and so I'm just providing this here, but what I'm going to do is we're going to plot this here. Okay, we're going to plot this because this is basically both. This is the function of echo time that the contrast noise ratio is, and this is really going to help you determine how to pick your echo time. So this is for different T2 star values. So T2 star values from 10 to 30 to 50 to 70 milliseconds. And it turns out that your maximum contrast noise ratio occurs when you set the echo time equal to the T2 star. Okay? So at 3 Tesla, T2 star of gray matter is about, let's say, 50 milliseconds. Okay? So according to that logic, let's look at that curve. So that's this curve here. So you see it has its peak at 50 milliseconds. So according to that logic, we should be acquiring our fMRI scans with an echo time of 50 milliseconds. But if you look at most protocols, we're down at like 30 milliseconds or 25 milliseconds. Okay, so why is that? Well, if you look at this curve, there's not much penalty. If I go down to 30, I'm only here. So the nice thing is that curve is actually pretty flat. Okay, and what that does is, so we can move down the curve quite a bit, and what that allows us to do is we can go faster now. We can, instead of waiting around for 50 milliseconds, even just going, that might not seem very much. We're only saving 20 milliseconds, but when you're trying to go through the whole brain as quickly as possible, it all adds up, right? If you're doing 30 slices or 40 slices, and you can save 20 milliseconds, that's like 800 milliseconds. That's almost, what is that, 40 times 20? Is that 800? That's a lot of time, right? Okay, so that's the reason why you're seeing we're actually using an echo time that's shorter than what's quote optimal, but it's actually pretty darn good. Okay. Okay, so now that before we have questions, I'm going to open up the first in-class exercise. So are there any questions before we have you guys do these fairly simple questions? Okay, so let me publish that now, and I think you have up to 3 minutes to do it. So those of you who have access can start entering your questions now. And by the way, feel free to talk to your neighbors on these in-class assessments. So if you want to discuss it, feel free to discuss it amongst yourselves. Okay, let's wait about another minute. So if you haven't entered in, do it in the next minute.
So your contrast could be how if you have more noise, so this decreases the ratio. So it's like oh yeah, I get it. Oh, it's just the same time. It's like it's not actually. Okay.
Okay, let's talk about this. So this is great. So for the first question, let's say about 36% said increased, 57% said decrease, and 7% said no answer. So let's take a look at that. So it turns out the answer is increase. Okay. So we need to talk a little bit. So obviously that didn't come across why that is. So remember we said that the percent change, the delta bold over bold, is approximately equal to minus delta R2 star times the echo time. Okay, and this is typically negative, so this whole thing will be positive. So if I increase this echo time, the percent change is just going to get bigger and bigger and bigger. Okay, so it's going to increase. And as we talked about, that's sort of meaningless at some point because it's only getting bigger because the bottom is going towards 0. Okay, but over a certain region, it's actually quite useful, and we might get to multi-echo fMRI sometime in the course. So over some region of interest as echo time, the percent bold change does increase, and that echo time dependence actually you can use to do some denoising, which we may talk about later. Okay. So it is useful to know that the percent change does increase with echo time. For the second answer, the correct answer is, well, there was 38% that said increase and 63% that said decrease. The correct answer is decrease. Okay, so at least we had the majority with the correct answer. And once again, think about it this way. If I have two signals decaying at different rates, if I wait too long, right, and this is as the echo time becomes very large, at some point they're both going to go to 0. So there's no difference. There's no contrast to noise ratio. Okay, and so the contrast noise ratio for fMRI always looks like these curves here, where it sort of goes up, has a peak, and then it's going to decay away. So there's going to be some optimal echo time, and it's fairly flat, but if you go too far out, it's going to go to 0. And so that's not So that's bad for two reasons. One is you have much worse signal noise ratio. Secondly, thing is your scan's much longer now. So it's like a lose-lose. Okay, so you never want to do that. All right? Okay. Any questions before we move on? Okay. All right. So let's talk now about some of the biophysics of what R2 star depends on. So R2 star is sort of the fundamental thing we care about. And so we're just going to give you sort of an overview of what are the factors that cause R2 star to change. And the bottom line is it depends on deoxyhemoglobin. And so the key is in the, let's see, in the lungs, so this is like in the lungs, you've got these oxygen. So the red things are representing oxygen atoms. And so they're binding to your hemoglobin. Okay? Now, as you go into the brain, that oxygen gets used up. And so it exposes the core of those deoxyhemoglobin molecules. And these are iron atoms. Okay? And so iron, as you know, is magnetic. So it's going to perturb the magnetic field around it. So it's going to cause the spins to get more out of phase. All right? So let's take a look at a picture of this. So let's say we're in some baseline state. And so there's some deoxyhemoglobin, but it's not much has been exposed. So there's going to be some amount of deoxyhemoglobin, some dephasing, so you have some decay. Okay. Now here we've used up a lot of oxygen, so all the iron atoms are exposed. So there's going to be a lot more dephasing. You're going to have a much more decay. That's a higher R2 star. Okay. But we just said that R2 star decreases mostly with activation. So that means that this is more like the baseline state. And this is like the activation. Okay. So ironically, you might think that there'd be more deoxyhemoglobin when you're using your brain, but evolution has set up the brain such that there's actually less. So we want to talk a bit why that might be the case. Okay. So let's work through some of the bold signal equation and some of the factors that the R2 star is related to sort of proportional to how much deoxyhemoglobin is there. Okay. And that's related to some constants, physical constants. CBV stands for cerebral blood volume. So how much blood is there? Typically in any given sort of area of the brain in cortex, about 4% of that is blood. Okay? And then the concentration of deoxyhemoglobin also matters. Okay? So how much blood is there, and then how much deoxyhemoglobin concentration there is in that blood. And there's this beta factor which just accounts for it. Sometimes the blood is in big vessels, sometimes it's around small vessels. So on average, a good thing is to use beta about 1.5. Okay, because depending on where the blood is, the oxyhemoglobin is, it has a different effect on R2 star. So a lot of work done in the early 90s sort of suggests that beta is about 1.5 is good. So the next thing we want to talk about is oxygen extraction. So basically the blood goes in, right? And then oxygen is being extracted out into the tissue. And so that we quantify that using something called OEF, or oxygen extraction fraction. Okay. So we can say that the concentration of venous deoxyhemoglobin is equal to the concentration of arterial oxygen times its OEF. So the more that's extracted, right, the more deoxyhemoglobin there's going to be. All right. So this is the basic picture we have in mind. We've got blood flow bringing in oxygen. There's going to be oxygen being extracted out, right? And we call that rate the cerebral metabolic rate of oxygen. Okay. And CMR2 is just equal to the how much oxygen you're bringing in multiplied by how much you're extracting out. So that's supporting the metabolism, right? You're delivering oxygen, how much your delivery you're using some fraction of it. The fraction that you're using is what you're using for metabolism, right? So we put that together. We already said that the venous concentration was OEF times CO2 arterial. So now we can substitute for this these terms and write it as CMRO2 over CBF. Okay, so it's just the ratio of metabolism over blood flow, which sort of makes sense, right? If I have more metabolism, then deoxyhemoglobin is going to go up. If I have less, it's going to go down. The more blood flow I have, the more delivery of oxygen I have, so that's going to make deoxyhemoglobin go down. And the less blood flow I have, then deoxyhemoglobin is going to go up. All right? So the overall picture looks like this. We've got blood flow delivering oxygen. We've got metabolism using up the oxygen. The venous concentration is just sort of the ratio of those two, of deoxyhemoglobin. So if CBF goes up, deoxyhemoglobin goes down. If CMRO2 goes up, deoxyhemoglobin goes up. Okay? So what did we say happens in most fMRI experiments? Does deoxyhemoglobin go up or does it go down? Up? Okay, so if deoxyhemoglobin goes up, the concentration goes up, what do you expect to happen to the fMRI signal? So if the more deoxyhemoglobin goes up, the more iron there's going to be exposed, right? So the more dephasing, so it's going to go down, right? So we know for most things we get a positive volt signal, so deoxyhemoglobin is actually going down. So you think about as deoxyhemoglobin goes down, there's less iron exposed, so there's less dephasing, so therefore the fMRI signal goes up. So that's the basis of fMRI, what's going on. All right. So putting it all together, we have we said that R2 star was related to some constant cerebral blood volume times this oxygenation term, which we can now replace with this CMRO2 over CBF. So it turns out that this is what we measure, and we try to infer things about neural activity, but as you can see, it goes through this sort of complicated path in between. Okay. This is a nice cartoon that one of my grad students did many, many years ago that sort of helps get the point across. So in this case, you're having blood flow bringing in the oxygen. Okay. With neural activity, there's going to be an increase in deoxyhemoglobin. Okay. And that's actually going to give rise to what's called the initial dip, which you can see primarily in sensory areas like motor cortex and visual cortex. It's very hard to see in other areas of the brain. But it is repeatable, and you can sort of see. So initially, metabolism increases first, and so that increases deoxyhemoglobin, which makes the signal go down. But very quickly, the brain says, "Oh, I better give you more oxygen." So blood flow goes up by quite a bit. Okay, and so for deoxyhemoglobin level goes down, and therefore you get this big increase in the bold signal. Okay, and after the activity is over, there's this return to baseline with this sort of post-stimulus undershoot, which even 28 years after fMRI has been invented is still being debated what that is. Okay. Okay, so any questions before we give you guys the next set of questions? Yeah.
Is the rate of metabolism constant over time?
No, so it actually changes, right? So that's the idea is when you're doing a task, your metabolism increases locally according to how much brain energy you need. Yeah. So it can change on the order of seconds. So in fact, this initial dip here actually is that very quick change of metabolism.
But within that, does it change or does it?
Oh, no, yeah, it can, yeah. The actual time course of metabolism is still not really, I mean, how that changes can vary a lot from task to task, right? There might be a very sudden increase and then a tapering off, or there can be very gradual, and that will depend on what the brain is trying to do. Yeah. Okay, so let me open up the next quiz. So that should be visible now.
more oxygen, there's less deoxyhemoglobin. So then when you decrease the hemoglobin, this is just saying only this increase in pH. So this is just different places. So if you only have increased mineral output, then you have this low signal. But if you have high all of this, then you have a large signal. Yeah. Yeah. Oh, yeah, and then this one. Wait. This is high. Wait. So based on this, if this is high, this is ratio. So if this is high, and this is low. So it's decreased. So based on this, because this is raised.
Okay, let's take a look at that. So for question 1, there was about, I think the overwhelming majority picked increase. So that is correct. So basically, as CBF increases more, right, it's going to deliver more oxygen, right? So that's going to decrease deoxyhemoglobin and just make the signal go up more, okay? And then for the next question, it was about 77% decrease, 23% increase. So the correct answer would be decrease. This isn't the best question. It could have been worded a little better, but the best answer would be decrease. So the idea would be as CMR2 increases, it tends to increase deoxyhemoglobin. So that will tend to drive the MR signal down. Okay. So all the things being equal, it would be decreasing the fMRI signal. All right. So are there any questions on that? Okay. So let me see where we're going here. Okay. So I'm just going to tell you what the Bold signal equation is. So this is the Bold signal equation, which is I'm just showing it to you because it's a very frequently used model called the Davis model. I just want to show you that it's basically related to, it's trying to get the percent Bold change into this term M, which is what's called the maximal Bold signal, and it's looking at the relative change in blood flow and the relative change in metabolism. So it's trying to boil all that down to one equation where we can look at the actual effects of blood flow and metabolism on the percent Bold change. All right? But I'm not really interested in deriving it. It's there for you to look at. What we're going to do is more look at what this model tells us about what we should expect to see. And also it's going to point out some of the limitations of Bold fMRI that you should be aware of. So what it looks like is this, that basically here I plotted the percent change in CBF, okay, versus the percent change in Bold, okay? And you can sort of see it has this sort of nonlinearity, and it's trying to get up to some maximum level M. All right, and what it's saying is the more I increase that percent change in blood flow, the more the Bold signal is going to go up. So that's very consistent with what we just saw in question 1. Okay, so the model does say that that's true. Okay, but you can sort of see there's competing effects. There's blood flow and there's metabolism. As we said before, those have competing effects. All right. And so, so one thing is there are factors that can change the maximal Bold signal. So for example, as you get older, blood volume tends to go down. Okay, so as you get older, you would expect the Bold signal to go down somewhat. Even if the neural activity was the same, just because there's vascular changes, there are reasons why the Bold signal will go down. So so as you're looking at your studies, especially if you're doing things across age, this is something you need to be aware of, that the Bold signal is a neurovascular signal. It's dependent on neuroelectrical activity, but it's seen through the lens of the vasculature. So anything that changes the vascular system can cause the bold signal to change even if the brain is fine in terms of its electrical activity. Okay, so just a word of caution, and we'll try to present some examples of that later in the course as well. The other thing that can change is what's called the CBF-CMR2 coupling ratio. And this is basically the percent change in blood flow over the percent change in CMRO2. Okay? And it turns out that you can write the percent bold change as a function of your sort of normalized flow and this coupling ratio. Okay? So I'm not going to go through the math, but just give you an example of why this is something to keep in mind. So it turns out that the relationship between bold and CBF depends on that coupling ratio. So how tightly coupled CBF and CMR2 are is going to change your bold signal. Okay? So for example, if they're coupled with a coupling ratio of 2, then I'm going to have this bold curve. But if the coupling ratio is 3 or 3.5, you see for the same percent change in blood flow, I increase my percent bold change. Okay? So here again, if you thought, for example, neuroactivity was tightly coupled to blood flow, but this coupling ratio changes, the bold signal would change even though the neuroactivity hasn't changed at all. Okay? So, and there's some reason to believe that that coupling ratio is a neurovascular thing, which can change independently of what the neurons are doing in terms of metabolism. So this sort of slide sort of sums it up. So if I had a coupling ratio of 2.5 and a maximal bold signal change of 8, I would get this bold change for this percent change in CBF. Okay. Now, one thing that could happen is I could decrease my CBF from 60% to 40%, in which case it would make sense that the bold signal would go down to here. So this would give me a smaller bold signal change. Okay. But I could also get that same bold signal change by just decreasing the M, right? So that maximum bold M has gone from 8 to 6.3. Maybe overall blood flow has gone down because of age, and so the bold signal has gone down. Okay. I could also keep M the same, but just decrease that coupling ratio. So I've gone from 2.5 to 2.15. That's going to be less of a bold change because that decrease in coupling ratio means that now for every percent change in CBF, I have a much greater change in CMR2. So that CMR2 is causing that signal change to go down. Okay? In fact, if the coupling ratio was 1-to-1, under certain conditions, the bold signal would go away. So if they're very tightly coupled, then you'll actually have no bold signal. So the only fact that we have a center for fMRI is because that n is around 2 or 3. If it was anywhere like around 1.2, we wouldn't even have this center because there would be no bold signal to see. So the fact that nature makes it such that blood flow increases almost 2 to 3 times as much as metabolism is what allows us to have the fMRI signal. Okay? As that ratio decreases, that fMRI signal starts to go away. All right? Any questions? Okay, so this is the very last slide and your very last question. So this is what we're going to end on. Let me just open that up. So that should be visible now. Okay, let's take a look at this. So the vast majority of people chose C, which is the correct answer. So that's great. So let's just go over that. So basically, if I go from a 2-to-1 ratio to a 3-to-1 ratio, that means blood flow increases a lot more than it needs to, right? So I really wash out. I have much less deoxyhemoglobin, and so the change, I'm going to have a much higher bold signal. Okay, so that's good. So any questions on that? Okay, great. So I think that's it for today, and so Friday's the practical, and then we'll see you next Monday when we'll start sort of the fMRI statistics part.